Hi everyone, my name is Osman Güngör. I am a student in Sivas University of Science and Technology, and this video is for my homework, which is OCV. OCV means Open Course View, and it is for my course that has the name of Principles of Aircraft Engineering, and this topic is International Standard Atmosphere, ISA, the short name of it, prepared by Osman Güngör, as I said. Let's learn it. What is the International Standard Atmosphere? International Standard Atmosphere is a reference point. I will give a real example that you will make it understand. I will make it understandable for you. You have phone and your phone is on the table. On the table, we are referencing the table, and ISA is like that. You are describing the values of density, temperature, and pressure according to altitude. And when you are doing that, there are some formulas and some base values that, for example, at the sea level, uh, the density is a value, the temperature is a value, and the other thing is a value. And according to altitude, they are changing. ISA is modeled these changes according to altitude. Let's read that. ISA is a model and reference that represent the condition on the Earth. As I mentioned, we calculate the standardized values for key atmospheric parameters such as temperature, pressure, and density. And after this calculation, we can acquire other values that we need. For example, you are in 11 kilometer and you 11 kilometer from the uh, sea level, and you want to know your density, temperature, and pressure at that altitude. To know that, there are some formulas to calculate them. It's very important, and as I mentioned, these values are very important for an aircraft engine, and the performance of uh, performance of engines depends on these values. Yes, this is the symbol of International Standard Atmosphere, ISA. Yes, I said that is a has some base values, and we are calculating the other values with this base value. This question is important. What is the value of temperature, density, and pressure at sea level according to ESA? At sea level with standard condition, the temperature is 288.16 Kelvin, which is equal 15.16 Celsius degree. We will use the Kelvin in most problem because in international standards, the standards standards unit is Kelvin. The density at sea level is 1.225 kilogram per meter cube. It means for each 1 meter cube, there will be 1.225 kilogram mass. Pressure is as I wrote that at the sea level 101325 Pascal, which is equal and 1 Pascal is equal 1 Newton over meter uh, cube, not meter cube. In fact, meter square, there is a mistake. It should be square. Yes, they are very important because, as I mentioned, we will find other values with these values. And for example, your base values from 0 to 11 kilometer will be these values. So it's very important. What is the logic of ESI? The ESI divides into some layers based on their altitude, and I will show the layers in coming slides. As you see, there is a photo of Earth, and this photo shows two layers of the atmosphere. The first layer is troposphere, the second layer is stratosphere, third is mesosphere, and the fourth is thermosphere. The last one is exosphere. In the ESI, we are usually considering the from troposphere to thermosphere. The layers are troposphere, stratosphere, mesosphere, thermosphere, and exosphere, as I mentioned. And there are some altitude, and there will be some interesting thing in coming slides. I will represent them. The graph of altitude versus temperature. As you see, this graph is altitude versus temperature, as you see. And if you go right, your temperature will increase, and if you go left, your temperature will decrease. As you can see, in it and at this region, from 0 to about 10 kilometer, 10,000 meter. This is troposphere, and at the troposphere, the temperature is decreasing according with increasing the altitude. There is an extra word that you should know. We will see these rates as a lapse rate. Lapse rate is the changing the temperature according to altitude. For example, if you go 1 kilometer from sea level to sea level to above, and if the lapse rate is minus 6.5 Kelvin per kilometer, your temperature will decrease 6.5 Kelvin, because you go 1 kilometer above the sea level. And as you can see, sometimes it's decreasing, sometimes it's increasing, and sometimes it's not changing. The interesting areas are them, because it's very interesting, and you are going high, but your temperature doesn't change. And at these areas, we say lapse rate, which is a equal 0. This means whatever you go from you go above, your temperature will not change, and because of that, there are two main formula for each pressure and density, because one formula has a lapse rate, one formula doesn't have. So if you have lapse rate equals 0, you will use another formula, and these formulas I will give in coming slides. The first layer is troposphere. Troposphere is the lowest layer of ESI, as you saw the picture which I showed you before slides. The first layer is troposphere. Its altitude starts from 0, which means sea level, to about 11 kilometers above from the sea level. At that layer, temperature decreases with altitude with the range of about 6.5 Celsius or Kelvin per kilometer. The units are very important, as you see on the graph, which means if you are decreasing with altitude, your lapse rate will be minus 6.5 Kelvin per kilometer, which means minus 0.0065 Kelvin per meter. The units are very important, and we will use these formulas. Do not do not mix or do not make mistakes with units. Other layer is stratosphere. It is the second layer. It's above the troposphere, and its altitude starts from 11 kilometers to 15 kilometer above the sea level. At this interval, you will see there is an isothermal region, and I will give the altitudes of isothermal regions or other region in coming slides. Between the stratosphere and troposphere, there is a region, as I mentioned, that the temperature doesn't change and constant. This means the lapse rate is equal to zero. We call it an isothermal region. It starts from 11 kilometer to 25 kilometer. This means, for example, you are in 12 kilometer and you are going away and going to, let's say, 19 kilometer, your temperature will not change, but other things will change. I will explain it. After the region, the temperature is increasing until 47 kilometer because of the ozone. Uh, it contains the ozone layer, which absorbs and scatters ultraviolet radiation from the sun. It is the reason that it is the reason that we say temperature is increasing until 47 kilometer. The other layers are mesosphere and thermosphere. The mesosphere extends from about 15 kilometer to 85 kilometer. Thermosphere is between 85 kilometer and 120 kilometer. In the mesosphere, temperature decreases from 53 kilometer to 71 kilometer. Uh, in fact, you will see them on the graph, and I will explain it with details in coming slides. They are just one. I want you to uh, prepare the base of this topic to understand incoming topics. From the graph, we can see these areas and variation. Let's learn it with detail. Yes, as I mentioned, lapse rates with altitude. Lapse rates, as I said, the change of temperature according to altitude. Between 0 kilometer to 11 kilometer, the lapse rate is minus 6.5 Kelvin per kilometer, which is equal minus 0.0065 Kelvin per meter. We will use probably and commonly these values, which is equal minus 0.0065 Kelvin per meter, not kilometer. I wrote it falsely. It should be meter. Between 11 kilometer to 25 kilometer, there is an isothermal region, which means the lapse rate is equal to zero. Between 25 kilometer to 47 kilometer, the lapse rate is positive. It means it's increasing. Positive 3 Kelvin per kilometer, which is equal 0.003 Kelvin per meter. Between 47 kilometer uh, to 53 kilometer, there is an also isothermal region, which means, as I said, lapse rate is equal to zero. Between 53 kilometer to 79 kilometer, lapse rate is also minus, which means the temperature is decreasing with altitude, and the lapse rate is minus 4.5 Kelvin per kilometer. Between 79 kilometer to 90 kilometer, there is an isothermal region, and between 90 kilometer to 120 kilometer, the lapse rate is 4 Kelvin per kilometer. And these values are and these lapse rates are very important. We will use in solving the problem. Yeah, calculating the density, pressure, and temperature with ESI. Temperature, the formula of thousand, which represented T1 equal T0 plus lapse rate times the difference between the difference of your altitude. This means this T1 is your temperature that you want to know, and this T0 is the base value, this A is lapse rate, and as I said, this is the difference of altitude. A is the let rate, as I said, the rate of changing temperature with altitude. T1 is temperature that we wonder. T0 is the temperature at sea level. Uh, H is altitude. If we use this formula, we can evaluate the temperature with altitude which we want to know. It's very important. And the formulas are very important. Pressure formula. When A is not equal 0, it's very important. When A is equal 0, these formulas will change. When A is not equal 0, P over P0, which uh, P means that you wonder the pressure at some altitude. This P is that. P0 is the base value. If you want to know the pressure at, let's say, 5 kilometers above the sea level, you should use P0 as the base value at sea level, which is equal 1.01325 Pascal, and the formula is P1 over P0 equal T1 over T0 to the power minus G over A times R. This formula is very important, and I solved a problem. In coming slides, you will understand it better. R is constant, A is lapse rate, G is gravity, R is 2089. It's constant, as I said. A is lapse rate, G is gravity. Uh, in fact, with altitude, the gravity is also changing, but we are neglecting it. Also, we know P equal rho. It's D means rho. It's density. RT. It's very common formula, and you have to know that D is density. Rho. It should be rho. So we can rewrite the formula for density rho1 over rho0 equal T1 over T0 to the power minus G over A times R minus 1. The difference is minus 1. If you want to know where does this minus 1 come from, if you use this P equal rho RT, and if you substitute this in the first formula, you will see R is constant, and yes, R is constant, and there will be T over T 0, and if you bring it with the opposite side of the equation, you will see there should be a minus. Yes, that's it. When A is 0, what should we do? The formula is P over P0 equal D means rho, which is density, rho over rho 0, which means the rates are equal A to the power. A is constant. It's about, as I'm not mistaken, 2.71 blah blah blah, and uh, as I said, it's equal A to the minus G over RT times h times the difference of altitude. As you can see, this power is all these expression is the power of A, which is 2.71 blah blah. In this part, P0 and D0 is the last part values, which means if you go, for example, 14 kilometer, your base values will be 11 kilometer, not at the sea level. It's very important, very important in fact, because you will, for example, if question asks you find the temperature, density, and pressure at 70 kilometer, you should know that. What is the temperature, density, and pressure at 14 kilometer? We will solve a question. It's the question. Firstly, base value for 14 kilometer is the values of 11 kilometer, as I mentioned. at 11 kilometer. T0 is temperature at sea level. H0 is initial altitude, which is 0 for now, because we will evaluate these values for 11 kilometer. We should use the Tyson formula, which I wrote in there. And if you use that, T will be equal 288.16 minus 0.0065 times 11,000. And you should know this 11,000 is meter, and this is lapse rate, and this 2,000 288.16 is the T0, and which is equal 216.66 Kelvin. Now we can use the formulas for density and pressure at 11 kilometer. This is the formula as I wrote in there, and if you write this T, which is equal to 260.66, and if you do that, this calculation will give you that your temperature and your pressure at 11 kilometer is equal to 671 Pascal. And as I said, this is the value at 11 kilometer. And if you want to know the density, you should use this formula. This formula I wrote and I explained the main of this formula, idea of this formula. And if you do calculation, the rho, which is equal density, will be 0.3645 kilogram per meter cube. These values, as I said, are the base values for the altitude of 14 kilometers. In coming slides, we will find the temperature, density, and pressure at 14 kilometers, with taking the base as 11 kilometers. At 14 kilometer, or P0 will be this value, which is equal to 2671 Pascal, and rho 0 will be 0.3645 kilogram per meter cube, and H0 is equal 11 kilometer. As I said, it's the base value, and you know the lapse rate is equal 0, so the temperature doesn't change. The lapse rate is equal 0, the temperature doesn't change. For pressure, we should use this formula, and as I said, the formula is changing. So if you use this formula, and if you write the values in this formula, you will see that the pressure at 14 kilometer will be 14129 Pascal, and as I said, the density and pressure formula are almost the same. And if you write values for density, you will see your density at 14 kilometer will be 0.228 kilogram per meter cube. You can see that with altitude also there is a very big difference. We cannot neglect it when we are flying. In summary, at altitude 14 kilometer, temperature is 216.66 Kelvin, which is equal with the 11 altitude. Density is 0.227 kilogram per meter cube. Pressure is 14129 Pascal. Yes. Yes, dear friends, that's it. As I said, my name is Osman Güngör. This video is for my OCV homework, open course via for Sivas University of Science and Technology, and I am a student of this university. Thank you for watching.